Welcome back to The Explainer. Today, we're tackling a topic that honestly makes a lot of physics students want to completely pull their hair out. But stick with me, because by the end of this, you're going to see it as this incredibly elegant puzzle. We're literally taking the sheer complexity of two-dimensional physics and transforming it into totally simple one-dimensional math. So if you've ever felt completely overwhelmed by objects flying through the air, moving forward and falling down at the exact same time, you are absolutely in the right place. Demystifying 2D motion, using the divide and conquer method. All right, let's dive right into a really visually striking scenario. Picture a bowling ball, and it's rolling straight off the edge of a 100-meter cliff. Now, it's got this initial horizontal velocity, right? Meaning it's moving forward. But the absolute second it leaves solid ground, gravity immediately kicks in and starts pulling it down. Which brings us to a massive core question. How can we possibly calculate exactly where that ball lands when it's moving in two completely different directions simultaneously? The horizontal motion is pushing it out, right? While the vertical motion is aggressively dragging it down, creating this swooping curved path. And trying to calculate that entire curve all at once, it just looks overwhelmingly complicated. But don't worry, we've got a brilliant trick for this. So here's our roadmap for the explainer today. We'll hit 1. The 2D problem. 2. Resolving vectors. 3. Adding vectors analytically. 4. Projectile motion in action. 5. Calculating displacement and velocity. And finally, 6. When projectiles aren't projectiles. Let's kick things off with section 1, the 2D problem. Two motions at once. Okay, the absolutely crucial point you need to grasp here is that perpendicular motions are completely independent. Seriously, this is the philosophical secret behind these analytical methods we use. It literally means that whatever is happening horizontally has zero effect on what's happening vertically, and vice versa. Sure, they're happening at the exact same time, but they do not mess with each other at all. And because of this magical rule, we can just use simple geometry and basic trigonometry to separate any complicated diagonal motion into two independent, totally manageable parts. Moving right along to section 2, resolving vectors into components, the x and y axes. Now, take a look at how a single diagonal motion, that vector labeled A, gets separated into a perfect right triangle. See, instead of dealing with that tricky, angled vector A as one big mess, we just create strict horizontal and vertical legs, AX and AY. And by doing this, boom, we've literally just turned one wildly difficult 2D problem into two incredibly simple 1D problems. If that whole triangle thing feels a bit too abstract, let's think about this fantastic walk-around-the-block analogy. Imagine you're trying to get to a coffee shop. You could cut diagonally across a giant empty lot, and that shortcut, that's our vector A. Or, to get to the exact same spot, you could just walk 9 blocks east, turn 90 degrees, and walk 5 blocks north. You can always break a diagonal path into simple, straight lines on a grid. It's such an intuitive idea, and it's basically the entire foundation of these analytical methods. All right, section 3, adding vectors analytically, a step-by-step guide. Let's quickly walk through this precise 4-step process. Step 1, you just identify your x and y axes. Step 2, you separate all your different motions and add up the components along the same axis. So you lump all the x's together and all the y's together. Then, step 3 is kind of the magic moment. You take that total x and your total y, and you use the classic Pythagorean theorem, a squared plus b squared equals c squared, to find the final total magnitude of your brand new right triangle. And finally, step 4, you just use some simple trigonometry to find the specific angle or the direction of that final motion. It really is that straightforward. Which brings us to section 4, projectile motion in action. Applying the theory. This comparison right here brilliantly illustrates our divide and conquer approach. We are literally splitting our calculations into strict, totally independent x and y columns. Think about it. In the x direction, there is no gravity pushing you horizontally, right? So the horizontal velocity is totally constant. But hop over to the y direction, and gravity is just constantly pulling the object downward, which creates vertical acceleration. By splitting the problem down the middle like this, we managed to keep these two completely different realities perfectly separated. Let's check out a fun, real-world scenario. Imagine a kid shooting off the very end of a water slide, perfectly horizontally at 4.2 meters per second, and they're facing a 3.2-meter drop into the pool below. Now, because they launch perfectly horizontally, their initial vertical velocity in that y column, it is literally 0. Gravity is the only thing doing the work vertically, and it's acting completely independent of how fast that kid is shooting forward horizontally over the water. Or, okay, how about this super quirky problem from the source text? Mrs. Swanson throws a tomato horizontally out of a 10-meter high window at 3.0 meters per second. And the problem asks exactly where Mrs. Reichling needs to stand on the ground to catch it. Well, by dividing the problem, we just use the y column to figure out that the tomato is in the air for exactly 1.4 seconds. Then we take that time, plug it right back into our x column, multiply it by the 3.0 meter per second horizontal speed, and boom, we find out the catcher has to stand exactly 4.2 meters away. Two totally separate, super easy calculations giving us one perfect real-world answer. How cool is that? On to section 5, calculating displacement and velocity. Hitting the ground. Let's look at a slightly more high-stakes scenario. Picture a helicopter flying perfectly horizontally at 25 meters per second, and it drops a mail bag from 15 meters up in the air. Now, the absolute instant that bag drops, it already has an x-direction velocity of 25 meters per second, just from riding in the helicopter. But now it's also instantly gaining y-direction velocity because gravity is pulling it toward the ground. So, the big question is, how fast is it going when it actually hits the ground? Well, notice how the bag completely maintained its 25 meters per second horizontal speed. That forms the top leg of our right triangle. Meanwhile, gravity accelerated it downward to 17 meters per second vertically, making up that downward leg. To find the final angled crash velocity, we're just recombine them using step 3 of our analytical method. Yep, the trusty Pythagorean theorem. You just square the 25, square the 17, add them up, take the square root, and just like that, we find the final impact velocity. It all comes together so beautifully. And that brings us to our final stop. Section 6, when projectiles aren't projectiles. The ultimate rule. I actually want to pose a question directly to you right now, just to test if you've truly grasped the foundational definition we've been relying on this entire time. Really think about it. An airplane is flying through the air, right? It's moving horizontally, and it's definitely being pulled down by gravity. So why is an airplane moving through the air not an example of projectile motion? Take a second. And here is the ultimate punchline. A true projectile, by the strict physics definition, only has the force of gravity acting on it once it is up in the air. That is exactly why our x column always had constant horizontal velocity, because literally nothing was pushing it horizontally anymore. An airplane, on the other hand, has roaring engines providing constant thrust, just constantly pushing it forward. So if an engine is pushing it, it's powered flight, not a projectile. So the next time you're outside and you see a baseball being thrown, or I don't know, a bowling ball randomly rolling off a cliff, or an airplane flying way overhead, I want you to ask yourself, is gravity the only force at play here? If it is, you now know exactly how to divide, conquer, and perfectly calculate its path. Thanks for hanging out and figuring this out with me today. Keep questioning the physics of the world around you because who knows what puzzle you'll unravel next.